In this video, I'm going to show the image of y-wing equation in the third system. Before y, do you know when do we need equation? Or do we need equation for 15 dB loss channel? You might say yes. Probably you need to ask me to provide more information about what I mean by the 15 dB loss. For example, if the loss was constant over frequencies from a simple resist divider R1 and R2 network, you may not need equation at all. As you can see, the frequency response is flat over the frequencies. Furthermore, the time domain waveform or the eye diagram shows good signal integrity without any distortion. Before and after the 15 dB loss, the shape of the time domain waveform or eye is the same. The only difference is the magnitude of the vertical voltage swing, which is probably still large enough after the 15 dB loss. Again, I did not describe the conditions well, and I should say, do we need the equation for 15 dB loss at the Nyquist rate, which implies the channel loss is frequency dependent and not flat over the intrinsic frequency. Let's take the RC network for example. The loss is greater as the frequency is increased. Therefore, most channels have frequency-dependent loss at the high frequency, as this simple RC network example, and we may need the equation. Otherwise, the time domain waveform or eye diagram shows poor signal integrity over close eye after the 15 dB loss at the Nyquist rate. Again, the very loss over frequency will cause the dispersion here. So, both the waveform transition and voltage swing are reduced greatly. Before we talk about the equation, let's understand the SerDes concept. In data transmission, we need to move the data from SOC A through a cable or channel to SOC B by serializing the data pair in, serial out at the source SOC and deserializing the data serial in, pair out at the destination SOC B. The pin counts or number of wires can be reduced greatly as we discussed in another video. In addition, the serializer and deserializer record SerDes over a C-link to a much lower power than the pair link in a long reach. Again, since the data transmission, the goal is to achieve an error-free or very low bit error rate at the receiver side. For the long reach SerDes, the equation is a must to achieve a very low bit error rate in transmission. After getting all the circuit image backgrounds, we can start to see what the bandwidth issue we might have. In the C-link, we may need a long reach or low cost channel. So, the channel's bandwidth tends to be lower compared to the Nyquist rate, and the inter-simple interference would be worse. The path rise-fall transition or the path shape in each bit is quite good before the channel. But the path after the channel has longer rise-fall transition time compared to the bit width, and the current symbol may interfere with the previous or next few symbols, which is so-called inter-symbol interference. After the superposition, the composite bit string showed the 2-bit 0 were the wrong level, and the bit error rate was increased. To resolve the ISI issue, we need to apply equation to make the bit error rate drop dramatically, which is the goal of the link transmission. We got a lossy channel below, and it has a higher loss as the frequency is increased, which may cause the signal integrity issue. So, what is the equation to deal with the low pass characteristic? Or what should be the equalizer's frequency response? Think about your own image for 5 seconds. Exactly. The equation is to generate the high pass characteristic to compensate for the low pass characteristic. You can put the equation blocks either before or after the channel, depending on how you implement it. So the idea is very simple and straightforward. To be clear, the equation's frequency response is the inverse of the channel, such that the total frequency response of the channel and equalizer will be flat over frequencies. Please be advised, this is just an example without considering the circuit impairments or constraints realistically. Instead, the mathematical example would like to provide you intuitive thinking of the equation, which equalizes the 0 dB in magnitude at all frequencies here. Again, in the frequency domain, it's obvious that the equalizer is to equalize the frequency content of the sampler's input signaling. Then, the signal at the sampler's input or channel output will have a good signal quality as the input of the channel. The goal is to help the sampler or comparator make the right decision easy by removing any channel's back frequency response. In the time domain, we can revisit the equation through the simple path response as shown here and look at the PRBS bitstream example in another video. The single path is transmitted before the channel with the sharp rise transition, so there's no intersymbol interference ISI occurring. However, after a channel, the path not only goes through extra delay time, but also has a longer rise-fall transition, which produces a long tail and the ISI issue. What's the ideal equation? Think about your own image for 5 seconds. Can we probably start with the frequency domain? Ideally, the frequency response of the output to the input transfer function will be flat in the 0 dB magnitude. What does the ideal frequency response imply in the time domain? Think about the image for 5 seconds. Yes, under an ideal equation of the time domain, the output path after a channel, an equalizer, or a sampler input would be the same as the input of the channel. The same transition rise-fall time and the voltage swing. Remember, the goal of the equalizer is to remove the channel's back impact and restore the signal's rise-fall transition time and swing exactly the same as the good one before the channel. So, the equation helps the samplers make a better decision by restoring to a bigger I width and I high. Again, please be advised, an ideal equation was only applied in the mathematical world, not the circuit implementation realistically. In the real circuit equation, the received path before the sampler input can be reshaped to have a faster rise-fall time, which reduces the ISI but is not being totally removed. Therefore, you can see the peak voltage of the path could reduce greatly, and the transition time would not be as fast as the input path of the channel, even though the residual ISI might exceed after the equation. The reshaped path is still much better than before. For example, you can see the path difference between the both cases without equation and with equation. This demo came from the CTOE case study, and we will revisit it later. Please be advised that there is no perfect equalizer to get rid of the ISI completely, and we must live with the residual ISI to some extent. The residual impairment concept is the same as the one of the DC offset cancellation in the algorithm design, which we will discuss in another video as well. Here is the summarized image you may have for the one obvious advantage of the equation: restoring the signal to the input of the channel Vin ideally. In other words, we want the output to be the same as the input of the channel is ideal fit-through without any distortion. In the frequency domain, we can cascade the channel's inverse frequency response to result in ideal fit-through, which is the 0 dB flat response over frequencies. Similarly, in the time domain, the cascaded path response of the equalizer can restore the V out to be the same as the V in, even though the path signal X after channel has the dispersion characteristics, which was attenuate in peak voltage and slow down in the transition. Lastly, the equation thus equals the total response to be equal to 0 dB over frequencies, and equals the final output path to the input path of a channel. Hopefully, the ideal equation image can help you have intuitive understanding of why you need equation in a SERDES system. Thanks for watching. Before you go, if you are benefiting from raw circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may benefit from it.